All right, they all have different birthdays. So I have 5 people. And we have to think about the number of ways in which they can have birthdays. The first person is completely unburdened. Their birthday can be any day of the year. Any of the 365, we assume 365. We don't get cute with leap years and stuff like that. All right, so first person can be born any day. You know, it's kind of like you're playing a game and you lose if your birthday is the same as somebody else's birthday. The pressure is off you a little bit if you're the first one selected, because then, like, it's your birthday that other people have to match up against. You don't have to worry about the stress of matching up to some already previously established birthday. Like, there is no burden whatsoever here. You could be born any day of the year. You're not going to be wrong. Right? The second person is going to lose this game if they're born the same day as the first person. So how many days can the second person be born? 364 out of the 365. There's only one day that they would have in common. If that second person's born on that one day, we got a problem. Any of the other 364 games are fair game. 364 days are fair game. The third person can't be born the same day as the first 2 people. So 363 possibilities for that person out of the 365 available. So it seems like the denominator is going to be 365 across the board. So I'll write that as 365 to the 5th power. And it seems like my numerator is decreasing by 1 every step of the way. In probability, once you get the sense of the trend, use that because it'll save you some work. Changing my colors here. All right. It's important because this question says on the probability that of 5 selected people, no 2 share the same birthday. But what if it said of 30 selected people? I mean, that's a lot of fractions to write, unless you can come up with a way to simplify it. So what this would be is a permutation, just looking at the top. We're starting here, and those fraction bars represent the number of slots, the number of positions, number of spaces, however you want to think of it. In which case, as a permutation, I'd have 365 P5. Right? Oftentimes, I just want the expression. I don't even want the answer. So I might say, write an expression that represents the probability that of 60 selected people, no 2 share the same birthday. In which case, this would be your final answer. Regardless of how I ask it, writing it like this, it's more user-friendly because this is something that's easier to put in my calculator. All right, so I'll create my fraction bar, alpha y equals n over d. Now I want to do 365 P5, 365 math, probability, option 2, pop in the 5, 365 on it, so hit the down arrow, 365 raised to the 5th power. So you get it all in one shot by writing it this way, and hit enter, and you get your probability. Okay, and so if we need a decimal value, it's about 0.973 if we're rounding. But pay attention to the instructions on the test because it's definitely in your best interest. Because rounding can be troublesome, and we don't want to deal with it often. So if you know that you can leave it in a particular form, then that's something you would want to know going in, right? And I'm not even talking about just a simple fraction. I'm saying if you know you can leave it as 365 NPR 5 over 365 to the fifth, that's just wonderful. Because then you don't have to worry about losing that half point for accidentally writing 0.972 instead of 0.973, right? So, it may seem like I'm trying to be nice and let you off the hook. I don't want to take off points for rounding and stuff like that. Really, I'm just trying to trick you into using proper notation, right? So I'm giving you the motivation to do that. So, if I don't put it in decimal form, then I don't have to worry about losing credit. Okay, he's a really nice guy. But meanwhile, you're actually using the proper probability and statistical notation in order to get your answer in the proper form. So I'm really the big winner here. So, but you get less point deduction, so you feel good about yourselves. Okay, so yes, I'm very mischievous. All right, part B, at least two share a birthday. Okay, so again, the wording is kind of strange. At least two people share a birthday. The first part was none of them have the same birthday. This is going to be 1 minus 0.973. Well, actually, I'm going to write it in notation form. 365 P5 over 365 to the fifth, which equates to approximately 1 minus 0.973, which again is approximate, but I'll write it equals, it's going to be 0.027. This one involves a little thinking because if you don't do the thinking, then you don't realize necessarily that there's that 1 minus relationship. The reason we can do this is because in order for at least two people to share a birthday, you need to have at least one pair of people with a birthday in common today. All right? Because, and it's a strange way to think about it. We're talking about people in the context of the problem, but in the solution to the problem, we're not talking about people, we're talking about birthdays. For possible birthdays, right? So in order for two people to have the same birthday, a single birthday has to happen more than once, right? And that's what this is really addressing, right? What this is saying is that there is never a repeat of a birthday. This is allowing for a birthday to be repeated, okay? So it's kind of a weird way to think about it, but it does have that at least one idea popped in there as part of the solution. So if you go back to, I forget what page it is, but it's the complement rule. It was the probability of none is equal to 1 minus the sorry, that was weird. Probability of at least 1 is equal to 1 minus the probability of none. I think it's like 4 or 5 pages ago. Then you can see what I'm talking about. But this is an application of that. So it's taking the two ideas and merging them together. But it's weird because you see at least two, and you don't necessarily think that it would be related to that particular rule. But if you think about it in terms of pairings, at least one pair of people with the same birthday, then it starts to fit. Right? So it's pretty strange, but it does work. And also, well,